In previous video, I explained insertion algorithm in B tree, and today I will dry run that algorithm with the example data, and also I will give the idea about the implementation of insertion algorithm in C language. Okay, so first see here this B tree I have taken, that is already I have drawn by inserting the number of data. Okay, now here I this for the degree for this tree t I have taken as 3. The degree of b tree, this b tree is 3. So minimum number of keys in this b tree is minimum keys can be stored other than root. Other than root, the minimum number of keys in any node can be 2, and the maximum number of keys are 5. Okay, so as the degree is 3, so t minus 1 number of keys will be stored in what? The minimum number of keys are t minus 1 except the root node, and 2t minus 1 for all the nodes, the maximum number of keys. Okay, so I have taken this diagram. I will tell you the concept of this root. Here there is a concept of header node, and as the size of the node can be equal to the size of the block, so here the header node contains only one field, the root, and root contain the address of the first node of the B tree. Okay, so for every algorithm T is pointer to the header node, and the header node contains one field, root, that contains address of the first node of B tree. Okay, so this is the B tree, suppose at any particular time. Now I want to insert this these keys in this B tree in the following order. Okay, so when I will take k equal to 54. So first I am taking k is 54. I want to insert k is 54. So according to our algorithm, first it will call, always we start from root, so from the main, just already tree is created, so simply just it will call the function insert. What insert function I described earlier in the B tree part 2 insertion algorithm. So here r equal to root 2. So whatever be the address in the root, just here I will pass. Simply I will call insert t, insert k and t. T is what? Here t. Okay, insert kt, and k is here 54. So simply r equal to root t. So this step, according to this step, r is pointer to this node now. Okay, so here the first this condition will check whether the number of keys in the root of the 2t minus 1, that is 5 or not, or simply it is checking whether the root is full or not. As I told earlier that for every insertion I will start from the root node and move to the leaf. Actually the key will be inserted at leaf, and in the path from root to leaf, if any node is full, then before moving down, first I have to split the node. The reason, when we split the node, the 10th key of the full node is moved to up. So before moving down, make sure that it is having one space that may accommodate the another key coming from the child. Okay, so here first it checks whether root is full or not. So in this case, number of keys in the root are not 5, so it is not full. So here if, so this nr equal to 2t minus 1, the t is 3, this condition is false. So here else part, control is transferred to else part, and insert non-full function is called. So this function is called. Here I have not written the split function. Insert non-full kr, insert non-full kx. So here simply the k is what 56 and x. Now this time in insert function, this is what x, because I passed here the value of r, and this is in this algorithm it will become x. So x, now x is pointing to the root node, and because here clearly it is mentioned that insert non-full. So when the control is transferred to this function, it is a guarantee that x is not full. Then only this insert not full function is called. So now I equal to nx. So here just what it is doing, simply it is checking whether first it is checking whether the x is leaf or not. If I equal to nx, and if it is here the x is not leaf, so simply I equal to nx. So I is 3. Here this piece of code is for finding the appropriate child in which k can be inserted. So it is started from the right. I is greater than or equal to 1 and k ix. So however, key to be inserted 54. So it will start from 90. So 90 is compared with 54. 90 is greater than 54. So here 90 is greater than 54. So I is decremented by 1. So the I is 2. Okay, again it will go, and now 40. The 40 is greater than 34. Again the condition is 40 is greater than 54. Its condition is false. 40 is greater than 54. 40 is greater than 54. So here the condition is, so 40 is greater than 54, the condition is false. So this condition is false. So now it will come out. Now here the value of I is 2. Value I equal to 2, this will stop, and now check whether the x is leaf node or not. Here the x is not leaf node. X is not leaf node, so again I will be initialized with nx. Now if it is not leaf node, this condition is if it is leaf node. So here it is not the leaf node. In this case, this is not a leaf node, x is not leaf node, so it will go to the else part. Else part, because the appropriate child in which the kth key can be inserted is I is what? I is 1, 2. So simply the third child, where the I is 2, so the third child will be the appropriate child where the key 54 can be inserted. So here first I have incremented I by 1. Here it will return 1 less than. So simply I equal to I plus 1. So now the I is what? 3. I is 3. Now discrete C3x, the third child of x is read from this. So this is what? This is C1, first child of x. This is C2, second child of x. This is C3. Okay. So C3 is the appropriate child in which the 54 can be inserted. Okay. So here the C3. So simply C3 is discrete. From this, when you implement that, this is not required that you have to write discrete. And if C3 x, now after reading the C3, the number of elements in C3 or the third child of x to be checked whether it is full or not. See, it is full. So here at this time it is not full. There are 3 keys and the maximum key is 5. So it will go to what? Insert not full KCIX. So this function will be called again, because as the C3 child is not full. So again this function is called. Now at this time K will become, K is 54 and X is in the next time insertion, this X is this. See? Now x is pointing to this node, and in the next time in the recursive call I equal to nx. I equal to nx. Now the number of keys, this code will find the appropriate child in which the 54 can be inserted. So just it will start I equal to 3. I equal to 3. So 80 is greater than 54. 54, so I minus minus, that is 2. Now 70 is greater than 54, so I minus minus, that is 1. 50 is greater than 54, the condition is false. So here the I will be 1. Now here it checks the condition whether the X is leaf or not. X is not leaf, so the else part is executed and I will be incremented by 1. Here I is 1, so simply for this X, the child C1, C2, C3, C4. So C2 is the appropriate child where the key 54 will be inserted. Okay, so now here I equal to I plus 1. So I is here 2. I will increment I by 1, that I is 2. So the second child. Now the second child will be will be loaded from the secondary storage device to primary memory, and then check it whether the second child of X is full or not. Here the second child of X is not full, so simply just it will call insert not full X K C KC2, I is 2, KC2 X. So now again the recursion continue, and now the X is pointer to this node. X is pointer to this node. So here now the insert non-full function is called with what? 54, and X is pointing to second child of X. Now I equal to nx, so I is what? Here I is 3. While I is simply just here the kix, I equal to I minus. This condition I can write the here we can write this condition before this code also. So here it will find the appropriate place for what? The appropriate place where the key can be inserted. So 52, 55, 60. So 56, 60 is greater than 56, so I minus minus, and 55 is greater than 55 is less than 56, so condition is false, so it will return I equal to 2. Now at this point here the leaf X, this condition is true. So now this is the node where I will insert 54, but before insertion it is required that because all the keys in a node are arranged in non-decreasing order, so just we have to find its proper place by shifting the key. So again here I is initialized with nx, so I is initialized with what? 3. I is initialized with 3, while I is greater than or equal to, so it will return 60 is greater than 56, so 60 will be shifted to the one location here. So here see, just this is the case 55 and 60, because this node can accommodate how many keys? 5 keys. So here the 60 will be shifted there, 60 will be shifted one place here, and now 55. So 55 is what? 55 is 60 is shifted, only one key shift is required, as it will return after that. So when it will return 3, 2. So second 50 is what? 55 is less than, so simply just 2. So here the 3 will be the proper third key will be the 54. So sorry, 55. So simply here the I is 2. I is 2. 2 is, I will start from 3. Okay, so 60 will be shifted as 60 is greater than 56. Now 55 is I will be 2, 55 is less than 56, this condition is false. So simply just here the proper place for the 54 is what? The third place. So simply I will be incremented by 1. Actually our data is 54, not 56, so correct it. So 54 is less than 55, so here one more time this loop will continue, and this is 1. So now the when this loop will terminate, so 1 is what? 52. 52 is less than 54, so here this condition is false and it will come out. Now I is incremented by 1 because the proper position is the second key position. So I will be incremented by 1, I is 2, key ix, x, the ith key of x will be k, that is 54, what is to be inserted. So here the 60 is shifted here, 55 is shifted here, and 54 is the proper place for here. So here 54 is inserted. So this is the case 54, 55. In this way this algorithm works. Okay. Now next key. So here this is the condition. Now next key what I want to insert is 56. Now the next key is 56. Okay. So previous key by mistake I used the term 56, but the previous key what I had to insert is 54. But now I want to insert the next key is 56. Again, just I will start from what? Root node R. This is R. Okay. Just now R is not full. R is not full, so insert not full function is called with K56 and this pointer to X. Here when the insert not full function is called, X is not full. Now simply it will find the appropriate child where the 56 can be inserted. So 90 is greater than 56, 40 is less than. So here, so I will start from 3. So 3 and 2. It will return from 2 as 40 is greater than. So proper child for 56 is a third child. So it will go here the insert function in the else part and this will become X. And here the second. Now simply the again insert not full function because the second child, this child is not full. Sorry, the third child where the 56 is inserted is not full. I will be incremented and is not full. So again the insert not full function is called with this 56 key and pointer to this node, and again that showed that the node is X is not full. Again we find the appropriate position, appropriate child. So 80 is greater than 56, 70 is greater than 56 and but 50 is less than. So I will start from 3, then 2 and then 1. Here this loop will stop at what? 1. This loop will stop at 1 as 50 is less than 56, or you can say 56 is not greater than 50. So the proper child, appropriate child where the 56 will be inserted is 2. So I, just here I equal to, I after this I have an I equal to, if it is not leaf, I equal to I plus 1. So I is 2. So the second child, and again the second child will be read from the hard disk and check it whether it is full or not. So here X is not full. So simply just insert not full. Okay. So insert not full. Now this is called. Okay. Again I will be initialized with 4 because now X contains what? The 4 number of keys. So I is initialized with NX, the from the last. 60 is greater than 56. So here the 60 is greater than 56. So I will be 3. Now 55 is less than 56. So here it will come out and simply this condition is true if leave X. So here this is the proper node. Always remember that in insertion algorithm, in B tree, the key always inserted at the leaf and you always start from the root for every key insertion, and in moving from root to leaf in the path, if any node is full, then first you have to split, then only move down. Okay. So now here I is 3. So third is the proper place where the 56 can be inserted. So here first move, first we find place the appropriate, we move the keys to make the room for 56. So here the I equal to NX, again I will be start with 4. The fourth key will be shifted to the 5th position. So here this is the case. what was here 50 okay, so first what the 60 is moved here. Okay, so simply 60 is here, so first 60 is moved here, then 55 is moved here. So simply just this is the proper place where the 56 can be. Okay, so 60 is 52, 54, 55 and 60. Okay, so here the 60 to be shifted here, that is 60, and simply just this is the proper place for 55. So here the 56 will be inserted here. Okay, so now this is insertion. So 56 is inserted here. Now just again I will dry run this algorithm for x equal to k equal to 62. K is 62. Okay, so again it will start from root. The root node is not full, so it will call the function insert not full. So this will become x and k is 62. Now simply it will find the appropriate child. I will start from 3. 90 is greater than 62, I minus that is 2, 40 is less than, so it will return I equal to 2. So simply just I will be incremented by 1, so the third child will be the appropriate child where the 62 can be inserted. So now simply just first it will read. So it will go on, because as this is not leaf, so simply this child will be retrieved from the hard disk and check it whether this node is full or not. So here this node is not full. So this node is not full. So simply what the 60. So this node is not. This node is not full. So simply it will find the appropriate child. So 80. Here now I am at this node. Okay? I am at this node. Again 80 is, I will start from 3. 80 is greater than 62, 70 is greater than 62, 50 is less than. So 3, 2, 1 I. So appropriate child will be what? Second child. Now from the hard disk, the second child will be loaded into the primary memory. Now just here at this point, this condition, at this point the simply just what child is loaded from the ith child. Ith child here means second child. Here the second child of, here the value of I is 2. Second child of x is full. So second child of I is full. So before insertion still it is leaf, but here the compiler doesn't know that this is leaf. Simply the second child is full. So first the compiler call what? Sorry, the operator it calls the split function. So simply this split function takes 3 parameters. Here I have not written explicit split function. I explained split function in the insertion algorithm part 2. Okay, so here the split function takes 3 parameter. X pointer to the node whose ith child, here I is 2, second child, and second child is C2x is full. So simply what split does, simply here this node, this full node, this is full node. This is what here, this is in the split function. If I am talking about the split function, this is y, this is x, and this is I. Ith child of x, ith child of x, y is full. So simply just splitting is performed. So here just one new node is created z, and t minus key 1 keys of y to be transferred to the z, and the tth key will be transferred to x, and so on. So after this what happened here, the 54, 52, 54 and 56, 60, 56, 60. Okay, this is the case. 56, 60, and now this is in this case, and 55 move, but 55 move only when I will shift what, all the keys and child pointers one location ahead. Okay, so here I am making, this is 55 and this is 50. So this this was 50, this was 50, and simply this is 70, this is 55. See here, this split part I explained earlier, C1, C2, C3. Okay, so now the C3 child of X will become Z, which is new node is created. So the full node is splitted into two nodes, Y and Z, and the Tth key, that is 55, shifted to X, and it maintains the search property that all the keys here greater than 50 and less than 55, here all the keys greater than 55, less than 70, and so on. Okay, now after splitting, just our key was 62. So 62, the proper place of 62 is what? In X, in Y, but Y is divided into two parts. So we have to check whether 62 will be in the Y or in the Z. So here simply it is this condition. K is what? 62. 62 is greater than what? 55. The Tth child जो ऊपर गया है अभी. So if the 62 is greater than 55, it means that you have to go to the Z. That is I plus 1. So I have updated here I is I plus 1. So I will become, previously I was 2. So now the I will become 3. I will become 3. It means the third child of X will be the where, and this function again called recursively to insert 62 in what node? In KCIX. That is, K is here what? 62, and CIX is what? I is 3, C3X. So now in this insertion function, this become X. Okay, so here I can insert 62. Okay, so simply what? This is what was here? The 60, 62 and 60 and 62. Okay, 56, 60 and 62. Okay. Now the next key is 57. Next key is 57. So here again I will move from the root. This node is not full, this node is not full, so the appropriate child is here. So 57 should be inserted because this node is not full by shifting. So this here, I am just removing this one, C3, and here the 57 is inserted. 57, 60, 62. Okay, this you draw this one. Okay, now again the K is what? 68. After this K is 68. So again the proper place for 68 is, this is greater than 55, so from here, so this is appropriate child. This node is not full, so control is transferred here. This node is not full, so control is transferred here. Now what? 68. So 68 will be shifted, 68 will be inserted here. Okay, now the next key is what? 58. Next key is 58. So when we insert 58, so again it will start from here. This node is not full, this is the appropriate child. This node is not full, this is the appropriate child. But now this node is full, so this node is full, so 60 will be moved up. So here simply 57. Okay, and this is what? 80, 70 and 60. Okay, so 60, left child is this one and the right child is this one. Okay, and the right child of 60 is this one, and 70 I have this, I have not disturbed this 70 and 80 here. The 70 and 80. So simply the 70, 80 and the right child of 70. I have not disturbed this one. Okay, so 70, 80. Only the 60 is shifted up. Okay, and the 60 sorry, 60, this is, okay, and 70 and 80, or here just the 90, okay. Now see, next key, suppose I want to insert say 58. So here the 58 is inserted. Now after splitting, the 58 is inserted. So 58 is inserted here. The 57, 58 should be inserted in this key. 57 and 58. Okay, 57 and 58. Now the next is what? The next key. Suppose the here what next key I want to insert is I want to insert, say, suppose 61. Next node to be inserted is 61. Okay, so K is here 61. So it will start from root. Root node is not full, so it will find the appropriate place of 61. 90 is greater than 61, 40 is less than, so C3. So I is 3. C3 will be the appropriate child where the 61 will be inserted. Now this node here, this node is full, so before moving down, first here this node will be splitted. So here again the 60 will be shifted up, that is here the 60, what was it here, this is 100, 60 will be shifted. So 60 will be shifted here, and this and 60, this will become the left child, this will become the right child, and 90 left child. This is 60. So 60 is shifted above. Okay. So now here just I explained how the insert not full and the insert function work. For every insertion I will start from the root. Okay. Now suppose I have not considered this case when the root is full. So suppose if the root is full, so what it does, simply just I will consider another diagram here. If suppose the root here, in this case the root is not full, root is 4, okay, but suppose the root is full, say suppose at any particular time, this is the case, like this is 20, 40, 60, 80 and 90. Okay, this is the case. And now here this is 10 and 12. This is 10, 12. This is what, the 22, 24, and this is 24, 42 and 50. This is 50, 60, 62, 670, and here 82, 85 and 95 and 100. Okay, suppose this is the case. T is equal to 3 and the minimum keys is 2. Now suppose here I want to add K equal to, this is the K equal to, this is a new B tree. Now K is 25. I have done this to check that when the root is full. So K equal to 25. So first it will call the function from the root what? Insert. This function will be called from the main insert. K, that is 25, and K, that is here 25, and T is simply the pointer. Okay, so what it does, first R equal to root of T. So R is this one. Now the number of elements in R in the root node is 2T minus 1. So here the root node is full. So what it is doing, S equal to allocate node. So memory is allocated for the node, and the pointer to this node is S. Pointer to this node is, one node is allocated, that is first see S equal to allocate node. Okay, so here I will allocate one node and the pointer to this node is S. Okay, now leaf of S is false. Of course, simply the child of S will become the R, so it cannot be leaf. So simply here the leaf status of S is set as false. It is not leaf. In S, as at present the number of keys in S are 0, so the number of keys in S is initialized with 0. Now the first child of S, now I will make the R which was full, just I will make this as first child of what, S1. So this is the first child. See, SC1S, S का जो पहला child है वो क्या हो जाएगा, R. Now root of T, I said that here there is a concept of header node. When the root is splitted, still only the root is not going to change, the address stored within the root will be changed. So here this statement, root of T equal to S. So here, now this is R, so root of T, this you can say the root, okay, and this is T, okay, this is T, so this is the case. Okay, here the root of T will point to S. Now carefully see the first child of S, which is R, is full. So here the split function is called split S1R. So S is simply that node which is not containing any element, and the 1 is the first child R. So split function, again what split function does? Split function split this key into this node into two parts, and the tth key will be shifted up. So what happened after the split? This is the case, and 60 will be shifted up. Okay, and here just 60 will be shifted. This is the left child of 60 after splitting, and this will become the right child of 60. Okay, so here this split function, okay, and split function this, and in the split function simply the 20, 40, 80, 90 we have to check what. Just now the problem is simply now S is not full, so now the problem is converted, so to insert 25 in S, so it will call K and S. So here this within insert function this will become X, and again this is the same as the insert function in a node when it is not full. Okay, so this is the about the insertion, dry run of the insertion algorithm. Now when you implement, if you want to implement B tree in any language, it is of difficult implementation. If you try, because there are not major changes, but if you are going to implement, I am giving the some idea if you are going to implement it in C language. Okay, so if you are going to implement C language, then see in this function everything is so here wherever I said earlier, wherever there is written as NX, all the statement to be converted into what? X is pointer to the node XN. If it is written as key I X, then this is converted into what? This is same as what? X dot key I, because for every node I am having what? The I number of there is an array, the key 1, key 2, key 3 and so on. Okay, and simply if it is written CIX, this is converted into what? X dot CI, means I am talking about the ith child of X. So these changes are required, nothing else. very careful. Here I have written I have not used the algorithmic assignment sign. So here I have written single equal. So here you use double equal. The same here you use double equal. Where I have written leaf x. So in the case of C language, there is not a concept of boolean. So simply I am taking 0 means it is not leaf and 1 means it is leaf. So here you can convert this that x dot leaf equal to 1. If this condition is true, it means x is leaf, and if this is equal to 0, it means it is non-leaf. Okay. Now another very important concept is the concept of root. What I said, here in B tree, the root node always in the main memory, and all other nodes of the B tree are in secondary memory. Okay. So what is the concept of here header node? So first I am giving the node structure. What I have given earlier: type def, struct nd, int n, number of keys that are currently stored in currently stored in any node, and int, this is the array of keys, key 2 into t minus 1, and int children pointer struct nd asterisk c 2 into t. Okay, and one more field is leaf. Here this is node structure. Okay, and simply I have used t as a degree of t. So here you can declare t as a constant using has defined t. Suppose degree is 2. So simply this. Now carefully note down that if here the t is 2, so it will allocate memory for 2 into maximum key. So this is the your node structure. Okay, so node structure means key 1 is what for the n, the second is key 1, key 2, key 3. So here I have written 2t minus 1. Suppose the value of t is 3. If the value t is 2, if the value of t is 2, then the maximum key 2 into 2 minus 1, that is 3. But in C language, it will go from 0 to 2. But here I have written the whole algorithm by taking the first key and with the index 1. Remember that here, so there is a null pointer assignment because I have not allocated the memory for the 2t minus 1 element e. So you always allocate. You can understand this in this way. Suppose if we declare int a5. If we declare int a5, then of course the memory for 5 elements have been allocated. But numbering is 0, 1, 2, 3, 4. But 5th element is not accessible. So here what I am doing, I am just allocating memory from 0 to, so for allocating memory 2t minus 1. So it will go on from what? 0 to 2t minus 2. It will go 0, 1, so on 2t minus 2. Okay, and I am trying to access 2t minus 1. So there is no memory. So here at the time of declaration, you declare the memory 1 more than the requirement. Region in C language, memory is allocated from the index 0 and I want it to start from index 1. So one change here, just what I have written in the earlier video, the node structure in C language, but you change that structure as the memory is 2t for the keys. Then if suppose t equal to 3, then simply 2 into 3 minus 1, that is what? 5 is the maximum keys. So here if we write 5, then it will go 0 to 4. 5th key will not access. So here I have written 2 into t, that is 6. Now it is okay. The 0th element of the key will be the garbage one. In the algorithm, I am not using it. The same here for the child. I will start from the C1, C2, C3. So 2t is required and simply we declare 2t plus 1. 2t plus 1. Okay. So this is the node structure. Now this is the structure of the node. Now I told that there is a concept of header node. As all the nodes, the size of the node is very large, depending on the degree of the T, and the degree of T can be the one block or one sector of the hard disk. So here as a root node always in the primary memory, so there is a concept of the header node, and header node is simply type def struct header node, and header node is having only one field, that is of type pointer to root. Okay, this is pointer to node, and the name is root, and here I am giving this head. Okay, so now simply when you write the main function for this insert, so you write what main, and here first you declare pointer, that is head. What here T is, see, T is pointer to the header node. And how many bytes will be allocated? Because there is only one field in header node, so only 2 bytes will be allocated. So first you allocate memory for T using what? Malloc function. T equal to node star malloc size of node. Okay, so simply the memory for node is allocated. Memory for root is allocated. Now we call this create function. This create function is called only once. This is for creating empty B tree. Here this is for empty B tree. So this function is called create T. Okay, create T. Now the control is transferred here. Now what it is doing? Create T is first allocating the memory. Wherever in the algorithm allocate node, you used malloc function to allocate the space for node. So R equal to allocate node. So one node is allocated and its pointer to R. This function is called at the beginning for creating empty B tree. Then nr equal to 0, of course the number of elements in the node is 0. Leaf of R, because this is the first node, so this will be the leaf. So leaf of R is true. Now root of T, see the root of T is, this is root and this is T. Okay, so root of T will contain this is T and this is root. So root of T will point to the R. Okay. Now the disk write R. Disk write function is not required when you implement the function, because when you implement then all the nodes and data are in primary memory. Okay. So here and now finally the create T function. Create T function will, after this create T function we call what? Here we are reading whatever you want to read, the number of keys is scanf. %d %k, and just you can give any criteria here. Here I am giving not equal to -1. You can give 99 or whatever with the terminating condition, and call the function insert kr. Here just insert kt, insert kt. Okay, at this time t is only declared to the kt, this function is called. That's why here the first time liking r equal to root t, this pointer to this node is passed, and here the root of t, and insert kt and scanf %d %k, and simply this is reading of all the keys. And after that you write a function traverse or print you traverse what from the root. So here you pass what t dot root. Okay, here I have written the program actually, so I have used t dot root. Okay, and now I am not giving the implementation of traverse. What you have to try to write yourself, how to print the B tree. Okay, So just one more thing, wherever there is a disk write, disk read, in the algorithm I have written disk read and disk write, as the B tree is designed for secondary storage device, and in secondary storage device the access time is more than the access time in primary memory. So the complexity of the algorithm is measured, complexity of all the functions here in B tree is measured in terms of disk read and disk write. So when you implement it in C language or in any other language, just remove all the statement disk write or here the disk write function. In the split function at the end I have written the three statement disk write x, y, z, so you can remove. So this is all about the implementation of insert algorithm. Thank you.